How's it going, everyone? Mr. Geyser here with the first video on Lesson 11 for logarithmic functions. For this series here, we'll be taking a look at 5 different skills and learning objectives, where first we want to try and understand the domain of a logarithmic function in general form is any real number greater than 0, and the range of that logarithmic function is all real numbers. 2, identify key characteristics of logarithmic functions and transformations. 3, determine whether logarithmic functions are increasing, decreasing, concave up, or concave down. 4, logarithmic functions do not have extremas except on closed intervals, and their graphs do not have any inflection points. And 5, we want to analyze and use limit notation to describe their end behavior. For these first couple of properties here, we want to try and elaborate more on logarithmic functions, where our goal is to summarize the key characteristics for logarithmic functions before moving on into properties of logarithms, solving logarithms and exponential equations, or even modeling with real-world behavior or real-world applications. Really, what we want to take a look at is first the domain of logarithmic functions, where we've shown that logarithmic functions have that general form of y equals log base b of x, is the inverse for an exponential function that equals y equals b raised to the power of x. And that is, what I mean to say, is that f of x equals b raised to the power, and f inverse of x is log base b of x. For our last lesson on inverses of exponential functions, for a function f and its inverse, f inverse, we have shown that the domain of f inverse equals the range of f. And the range of f inverse is the domain of f. So let's summarize all of those findings in 5 key ideas. The properties of the graph of a logarithmic function follow that the graph of a logarithmic function has that form of f of x equals log base b of x, where b cannot equal 1 and x is greater than 0. Other than those 2 rules, b and x can be any number at all, as long as b is not equal to 0 and x is not a negative number. It follows these 5 properties. The first property for all of those log functions is that their x-intercept is 1, 0, and there's 0 y-intercept. The reason why there's no y-intercept is because the y-axis, x equals 0, is the vertical asymptote of the graph. And if b is greater than 1, the function is increasing. However, if b is between 0 and negative, or 0 and 1, then the function is decreasing. If the graph of the function contains, if the graph fits this, then the graph contains 3 known points. 1, that 1, 0 for that x-intercept. 2, that b, that base, 1, and that 1 over b, negative 1. Finally, the graph is smooth and continuous. It has no sharp corners or gaps. Let's explore these properties in example 1 here. For these 3 parts here, we want to try and find the domain of each of these functions here. Where first, for part A, we want to kind of explore how we're finding the domain. My first step here is I know I don't want to have any negative numbers inside of my log function, where that base form there showcased that log base b of x, where the inside of x can't be 0 or negative numbers. So really what I'm just trying to say here is when the inside of these parentheses is greater than 0, or when x plus 5 is greater than 0, is going to give me some inequality. This inequality here determines the domain for that log, where the domain for this log is from negative 5 to infinity. Let's take another look at part B here. For part B, we're following those same steps. My first step here is to take out what's inside of this log here and make that inequality where it's greater than 0. Now I want to know when it's greater than 0 or when there's going to be some discontinuity. Well, right off the bat, I know that my denominator here cannot equal negative 1. It causes this to be undefined, so I just need to know in the back of my head that this version, this denominator, cannot be equal to, or x cannot be negative 1. For the numerator, I know right off the bat that I don't want my numerator to equal 0, because then that would make the whole fraction 0, which makes the inside of that log 0. So I know right off the bat that x can't equal 1. Kind of just like writing that out. Well, I don't want this to be a negative or this to be a negative, so I can write out these mini inequalities for those fractions, where I have 1 minus x is greater than 0, or 1 plus x is greater than 0. If I were to solve this out, I'm just moving that 1 to the other side to get negative x is greater than negative 1, multiply by negative 1, and I end up getting x is less than 1. These two things are equivalent. Same thing for these two operations here. I'm just subtracting 1, bringing it to the other side. And I know that for this top one, x can equal 1. Well, luckily for us, we're never going to reach that. We actually have an inequality where it doesn't even reach 1. Same thing for our denominator, where our denominator here never goes below negative 1. It's always above negative 1 here. But notice this confliction here. There's only a very small range that our x's can actually be. If they do happen to be anything other than 1, or between negative 1 and 1, it causes this whole fraction to become negative. So our domain, based on these inequalities, is between negative 1 and 1. Let's try that one more time for part C with these absolute values. For this absolute value there, we know right off the bat that we don't want this to be less than 0. In general, absolute values make it really easy for things to be not less than 0, but we do have some issues. First, let's make these mini inequalities where we have that version of x minus 2 is greater than 0, and then negative x minus 2 is greater than 0. This first inequality is pretty self-explanatory. You're just adding 2 to both sides to then get that green inequality of x is greater than 2. This second one's a bit more complicated. If you were to distribute that negative 1, you end up getting negative x plus 2. You then subtract 2 to both sides to get negative x is greater than negative 2. You would then divide or multiply by negative 1 to both sides, which flips our inequality. So in general, what we have is these two inequalities, x greater than 2 and x less than 2. What really we want to say for the domain here is it's all the negative numbers up until 2 and all the positive numbers from 2 onward where we do not include 2. The reason why we don't want to include 2 is if x was 2, we would get 2 minus 2 to get 0, absolute value is 0, and that just isn't greater than 0. So it's pretty self-explanatory. Now let's take it up a notch. Let's look at example 2, where in example 2, we want to try and pair these log functions with these given graphs here. We want to find the general behavior of some log functions based on their base and some key characteristics that's inside the parenthesis and outside that log. The graphs of the log functions are given. We want to match them to graphs A through D from one of the following equations here. Well, we take a look first at f of x. For f of x here has that base of 2. Since the base is greater than 1, we know it's growing. It's increasing in some way. Since we know there's no negative value in front of this x, there's no c value, we also know that it's going to be an increasing, or it's following that general form of log. So in general, for f of x, it's increasing. However, if we take a look at g of x, the only thing difference between g of x and f of x, base is the same, but its c value is actually negative. Since we have a negative x, we know that this here is going to be decreasing. A negative value on our x flips it about the y-axis. Now, if we take a look at h of x, we have the same thing as f of x, but that negative is on the outside of our log. If the negative is on the outside of our log, we have a reflection about the x-axis. Inside the log, y-axis. Outside the log, x-axis. Those are the reflections. But however, if we take a look at k here, and real quick, I apologize, for g of x and h of x, those are both decreasings. If there's ever like a reflection about it, and only a reflection, it causes the graph to decrease. So if we look at k of x, we happen to have that x, or that negative value inside of x there, which causes it to flip about the y-axis, which makes the graph decreasing. However, we also have a base that's less than 1, which makes it decay. Since it's a decaying graph that's flipped about an axis, it actually cancels each other out, and it makes an increasing graph, which is kind of funny. With this information now, we're able to try and spot which graph goes to which. I'm going to pause for a moment. I want you to take a guess which graph f of x is going to go to. A, B, C, or D. In 3, 2, 1. Did you get it right? This third one right here. It follows that general form where it passes through that 1, 0 point. It passes through that 2, the base of the log, comma 1, that just normal point there. Now let's take a look at g of x. For g of x here, make your guess. Is it A, B, or D? In 3, 2, 1. Did you get it right? That first graph there, it just happens to have that reflection about the y-axis. For the y-axis here, it really is just this f of x graph, reflected about the y. Keep that in mind when we take a look at h of x. Make your guess. Is it B or is it D? 3, 2, 1. Did you get it right? Our h of x happens to be B. It's just reflected about the x-axis. Notice how there's still things above and below our x-axis in both of these cases. In our y-axis case, the whole graph goes over into the negative realm. In our h of x case, where we're flipping it or we're reflecting it about the x-axis, the top section goes to the bottom, that bottom section goes to the top, and it makes this kind of decaying graph here. As a reminder, our g of x and our h of x here are both decaying kind of graphs. They both decrease over time. Leaving part D here, or that graph D, being for our k of x function here. For k of x here, we really just see that we have this increasing graph. It happens to have this decay of 1/2, but since it reflects about the y-axis, it actually starts to increase over time, kind of negating that decay. Now let's take a look at this bottom part here, where based on your findings, which graph above would also correct, or which of the graph above would also be correct for y equals log base 1/2 of x? Notice that we don't have one of these graphs on our k through g or k through f graphs. It's this function here. Which graph corresponds to that function there? Well, we can kind of do some analyzing with this graph here. We know that, well, 1/2 here, since 1/2 is less than 1 but greater than 0, the graph is going to be a decaying function. So we know it's not going to be k. We know it's not going to be f. It has to be between h and g. So really, what this is trying to get at is even though there isn't a negative in front of the x or in front of the log, because we have a fraction, it does the same thing as a reflection in some aspect. Well, let's try to manipulate this fraction a little bit. In general, we have these two different functions, our g of x and our h of x. And if I were to write these as exponential functions, my log base 1/2 of x equaling y gives me this exponential function, where these two things are equivalent. Our y happens to be in the exponent, which makes it kind of hard to see. But I just want to keep it there. These two things are equivalent. Our g of x is base 2 of y, which is now g of x, equals negative x. But let's take a look at h of x, where if h of x is equal to negative log base 2 of x, I can't really use that rock and roll method if there's a negative in front of my log. So I'm going to divide -1 to both sides to get negative h of x to equal log base 2 of x. Now, I find that it equals this equation, where I find that it's the base of 2 raised to the power of negative y of x. And since it's 2 raised to the power of a negative exponent, that's really the same as saying 1/2 raised to y equals x. And we can see that h of x here is actually equivalent to this base of 1/2, where the log of 1/2 of x is equivalent or equal to negative base of 2 of x, where that log there happens to be negative. Where we can say that this graph here corresponds to that graph on B. Thank you very much for joining me on this first video where we explored the properties of these logarithmic graphs by looking at example B, where we chose these 4 graphs, and example A, where we explored the domain of our log functions. I look forward to seeing all of you guys in that next video. Take care.